Every large motor on an offshore vessel has one small box standing between it and a catastrophic fiery winding burnout. Meet the ABB ACS6000c. Imagine you're deep in the engine room of a massive offshore rig. You're surrounded by roaring machinery, salt-heavy air, and millions of dollars of critical equipment. Down there, this one remarkably smart relay is the ultimate lifeline. The ACS6000c carries an absolutely massive responsibility. It's a numerical, multi-function motor protection relay serving as the ultimate failsafe for medium and large AC marine motors. And whether those motors are switched by standard contactors or heavy-duty circuit breakers, this compact unit is the brain making those split-second life-or-death decisions for a ship's electrical propulsion and auxiliary systems.
In this explainer, we're covering 5 key areas. First, the physical armor, the offshore motor's lifeline. Second, relentless self-supervision. Third, thermal and overcurrent defense. Fourth, earth faults and silent killers. And finally, customization through switch groups. Let's dive right in.
Section 1. The offshore motor's lifeline. The physical armor. Before we even touch on the software, we've got to talk about the brutal reality of a marine environment. Heat, oppressive humidity, and highly corrosive salt spray will degrade insulation and electronics faster than just about anywhere on land. That's exactly why this relay is housed in a rigid, IP54-rated aluminum case. Offshore ambient conditions aren't just a footnote, right? They're a primary design driver. This IP54 casing is specifically approved to lock out that harsh marine atmosphere, making sure the delicate microprocessors inside can safely command those contactors or heavy circuit breakers without skipping a single beat.
Section 2. Relentless self-supervision, the 5-millisecond heartbeat.
This is where we look past the metal casing and into the relay's internal brain. And let me tell you, this brain is wonderfully paranoid. Here's what separates this from a dumb overload relay: relentless self-supervision. The RAM runs a rotating one check every 10 milliseconds. The ROM relies on constant checksum verification. EEPROM read and read operations get strictly cross-checked. The AD converter, which translates raw analog currents into digital data, is verified every single minute. And at the center of it all, the watchdog, pulsing a heartbeat check every 5 milliseconds.
So, quick check. Let's pose a real-world scenario. Imagine the relay's internal EEPROM check fails quietly in the background. No alarms are sounding in the engine room quite yet. Would the crew actually notice this failure before a massive electrical fault hits the motor?
Yes, that's the entire purpose of self-supervision. The relay's own watchdog and diagnostic checks guarantee it will flag its own internal failure immediately, triggering an alarm instantly. Because the absolute worst-case scenario in power systems isn't just a motor fault, it's a broken relay silently failing to protect a motor when it's actually needed. Self-supervision eliminates that silent threat completely. It catches failures before the motor ever needs protection.
Section 3. Thermal and overcurrent defense, the primary arsenal. Let's look at exactly what this relay is protecting against with its integrated protection functions and ANSI codes.
It's important to understand that massive offshore motors rarely die instantly. Usually they cook slowly over time. Enter ANSI Function 49, the 3-phase thermal overload protection. This is your absolute core defense against slow, winding burnouts. It mathematically calculates the exponential thermal heating of the motor based on the current it draws over time. Basically, it mimics the physical heat building up in the copper windings, allowing the motor to work hard, but tripping it exactly before that heat degrades the internal insulation and starts a fire.
Then we have Function 14, which is stall protection. Imagine a massive pump ingests some debris and the rotor gets physically locked. The motor is screaming, trying to turn, drawing massive current, but going absolutely nowhere. Function 14 uses a speed switch input to realize the motor hasn't come up to speed within its strictly limited safe stall time, and it cuts the power before that stalled rotor completely melts down.
Notice the contrast in defenses here. On one hand, you have Function 50, which is your blunt instrument. This is the instant, high-set short-circuit trip. If a cable shears and dead shorts, Function 50 trips fast and hard. But starting a massive motor also draws a huge spike of current that looks an awful lot like a short circuit. That's exactly where Function 48/51 comes in. It's a highly nuanced, definite-time thermal stress monitor designed specifically to watch that prolonged starting sequence, making sure the motor survives the heavy start without any annoying nuisance tripping.
Section 4. Earth faults and silent killers. Current going where it shouldn't.
You see, not every fault is a massive, violent overcurrent explosion. Sometimes, the deadliest faults are the ones where current is quietly going exactly where it shouldn't be. And this is where function 51N becomes absolutely vital. This is the definite time low-set earth fault protection. A standard short-circuit overcurrent function completely misses tiny insulation leaks where just a few amps bleed into the ship's hull. But in a marine environment, moisture and salt inevitably cause these low-level leaks. Function 51N catches these tiny, dangerous earth faults long before they evolve into full-blown arc flashes.
Another silent killer is phase unbalance, which is monitored by function 46. If a vessel loses one electrical phase, or if the phases somehow get reversed, a simple overcurrent relay might not even notice, but the motor definitely will. It'll silently overheat, literally vibrating itself to death as it tries to pull all its power from the remaining phases. Function 46 catches this inverse time phase unbalance and shuts the whole thing down before the damage is done.
We also have function 37, definite time undercurrent protection. Now, you might be thinking, why on earth would too little current be a problem? Well, if a pump is spinning dry, or if a mechanical drive shaft snaps, the motor suddenly has no load. The current drops dramatically. Function 37 catches this sudden loss of load, which is absolutely crucial for preventing devastating mechanical failures downstream.
Here's something to keep in mind. A motor doesn't just cool down instantly once you turn it off. It takes a long time. The SPAN150C actually tracks this exponential cooling even when the motor is at a complete standstill. The restart inhibit counter prevents a stressed motor from being started over and over again. The relay only resets its cooling history back to zero when the motor's current drops below 12% of its nominal rating, indicated by the 0.12 times IE threshold. Basically, it forces the crew to let the hardware rest.
Section 5. Customization through switch groups, tailoring the logic.
You could literally have two absolutely identical SPAN150C relays sitting side by side, protecting completely different motors in entirely different ways. How? It all comes down to switch group logic. The relay's behavior is dictated by three distinct programming layers. We have SGF, which handles optional software behaviors, SGB, which manages the routing of blocking signals, and SGR, which handles the physical mapping of alarms to output relays. Let's break these down real quick. Starting with SGF, the switch group functions. This is what configures the optional behaviors. For example, some massive motors pull incredible amounts of current on startup. With SGF, you can tell the relay to automatically double the short-circuit trip threshold during the start sequence, or even inhibit earth fault protection if the current spikes above 4 to 8 times nominal. This is a real game changer because it prevents those frustrating nuisance trips during perfectly normal, heavy starting surges.
Next up is SGB, or switch group blockings. This is how the relay communicates with the outside world. Say you have an external digital speed switch on your motor, you'd route it right through the SGB. Or if you want a trip alarm to physically latch, meaning that red light stays on and the system stays locked out until an engineer physically walks over and resets it, you configure that exact behavior right here in the SGB logic.
Finally, we have SGR1 and 2, the output relays. This standardizes exactly where each software alarm physically goes on the ship. It forms the crucial bridge between the internal code and the hard wiring of the vessel. It lets you decide if a thermal warning just flashes a light in the control room via signaling output SS1, or if a stall condition physically trips the main breaker via trip output TS2.
This really sums up the entire engineering philosophy of this device. Identical hardware becomes a tailored, fail-safe guardian through the power of its configuration. The physical IP54 box is incredible, the 5-millisecond heartbeat is flawless, and the ANSI protection codes are rigorous. But ultimately, this device is only as good as the switch group logic that a skilled engineer programs into it.
Which brings us to our final thought. The sea is completely unforgiving, and the massive motors driving our offshore industries demand perfect protection. Knowing the deep technical capabilities of the SPM150C, from its relentless self-supervision to its silent killer detection and highly customizable switch group logic, how will you configure the brain of the next massive offshore motor you commission? Will you just leave it to the factory defaults, or will you engineer a truly fail-safe guardian? Thanks for exploring this fascinating technology with me today. Keep learning, keep questioning, and I'll see you in the next explainer.